The cosmic censorship hypothesis is an idea in physics that tries to explain how the universe hides its biggest mysteries. It says that singularities, which are places where gravity becomes so strong that the usual laws of physics stop working, are always hidden inside black holes. These black holes have a boundary called an event horizon, like an invisible shield, that prevents anyone outside from seeing or interacting with the singularity. This helps keep the universe predictable and prevents strange effects, like time running backward or cause and effect breaking down. While scientists have evidence that event horizons exist, such as images of black holes and the detection of gravitational waves, the true nature of singularities is still a mystery. Some scientists think that at very tiny scales, where quantum mechanics becomes important, singularities might not be infinitely small points, but something more understandable, like tiny quantum objects. The hypothesis helps us explore how the universe stays orderly, even in its most extreme and puzzling situations.
Part 1. Introduction to Singularities and the Cosmic Censorship Hypothesis. In Einstein's general theory of relativity, a singularity refers to a region in spacetime where gravitational forces become infinite and the laws of physics break down. Singularities are theoretically predicted to exist at the center of black holes and during the Big Bang. However, the concept raises significant questions about the nature of reality, as the breakdown of physical laws challenges our ability to predict or understand phenomena near such regions. To address this, the Cosmic Censorship Hypothesis, proposed by physicist Roger Penrose in 1969, suggests that singularities are always hidden within event horizons, ensuring they remain inaccessible to outside observers and preserving the predictive power of physics. Example: in a black hole, the singularity is surrounded by an event horizon, a boundary beyond which no information can escape, effectively cloaking the singularity from external view. Analogy: singularities are like forbidden zones in a video game, where entering results in undefined behavior, but barriers, event horizons, prevent players from accessing these regions. Singularities arise as solutions to Einstein's field equations, which describe how matter and energy shape spacetime. Under extreme conditions, such as those found in collapsing stars, the equations predict regions where curvature becomes infinite. This infinite curvature signals a breakdown in the mathematical framework of general relativity. Theoretically, two types of singularities exist: naked singularities, which are visible to external observers, and hidden singularities concealed within event horizons. Naked singularities would expose the universe to regions where causality and determinism fail, posing challenges to the foundations of physics. The cosmic censorship hypothesis posits that nature prevents naked singularities from forming, preserving the integrity of spacetime. Example: the Schwarzschild solution to Einstein's equations describes a non-rotating black hole with its singularity hidden inside the event horizon. Analogy: singularities are like mathematical paradoxes in equations. Solutions exist but defy interpretation under standard frameworks, and nature erects barriers to keep them out of reach. The cosmic censorship hypothesis is often divided into two formulations: weak cosmic censorship and strong cosmic censorship. Weak cosmic censorship suggests that singularities cannot be observed from infinity because they are cloaked by event horizons. Strong cosmic censorship posits that singularities are hidden even within spacetime itself, ensuring no physical laws break down in observable regions. The weak hypothesis aligns with observational evidence, as all known singularities are hidden within event horizons. However, the strong hypothesis remains speculative and is subject to ongoing debate. Example: the Kerr black hole, a solution describing rotating black holes, theoretically allows the possibility of a naked singularity if certain parameters are exceeded, challenging the weak hypothesis. Analogy: weak cosmic censorship is like ensuring dangerous machinery is always kept behind safety glass, while strong cosmic censorship ensures the machinery is not only hidden, but also rendered inaccessible to anyone inside the room. Event horizons serve as space-time boundaries that shield singularities from external observation. According to general relativity, no information, light or matter can escape from within the event horizon. This effectively cloaks the singularity, ensuring that its effects on spacetime are limited to regions inside the horizon. Event horizons are key to maintaining causal order in the universe. Without them, singularities could interact directly with the external universe, potentially disrupting the deterministic framework of physics. They also ensure that observers outside a black hole encounter only well-behaved spacetime, governed by predictable laws. Example: in the case of a Schwarzschild black hole, the event horizon is located at the Schwarzschild radius, beyond which nothing can escape the gravitational pull. Analogy: event horizons are like curtains around a stage during a play. What happens behind them is hidden, ensuring the audience only sees the coherent narrative presented on stage. Naked singularities, which lack an event horizon, represent a profound challenge to physics. Without the shielding provided by event horizons, the infinite curvature of spacetime would become observable, potentially leading to causality violations where effects precede causes. Naked singularities would also expose regions of spacetime where quantum and classical physics fail, necessitating new theoretical frameworks. While theoretical models, such as certain solutions of the Kerr metric under extreme angular momentum, allow for naked singularities, no observational evidence of their existence has been found. Their potential existence raises questions about whether the universe adheres to the cosmic censorship hypothesis or whether exceptions might exist. Example: the hypothetical Tipler cylinder, a rotating massive cylinder in general relativity, could create closed time-like curves, effectively exposing regions with causality violations. Analogy: naked singularities are like glitches in a computer program, unanticipated scenarios where the rules fail, leading to unpredictable outcomes. Observations of black holes provide indirect evidence supporting the cosmic censorship hypothesis. Astrophysical phenomena such as accretion disks, relativistic jets, and gravitational waves confirm the existence of event horizons, suggesting that singularities remain hidden. However, these observations cannot directly probe the singularities themselves, leaving their true nature speculative. Advances in imaging techniques, such as the Event Horizon Telescope, which captured the shadow of the supermassive black hole in M87, offer new insights into the behavior of event horizons. These studies suggest that singularities, if they exist, are indeed concealed within event horizons as predicted by the weak cosmic censorship hypothesis. Example: the detection of gravitational waves from black hole mergers by LIGO and Virgo provides evidence for the event horizons predicted by general relativity. Analogy: observing a black hole's event horizon is like seeing the edge of a forest. While you can infer what lies inside, the dense canopy hides the details of the forest floor. The cosmic censorship hypothesis operates within the framework of classical general relativity, but quantum mechanics complicates this picture. At extremely small scales, quantum effects dominate, and spacetime itself may become discrete rather than continuous. The reconciliation of general relativity and quantum mechanics, often referred to as quantum gravity, may reveal whether singularities are truly physical or merely mathematical artifacts. Quantum theories, such as string theory and loop quantum gravity, propose mechanisms to resolve singularities by introducing quantum corrections to spacetime. These corrections could replace singularities with finite structures, such as quantum fuzzballs or Planck scale regions, effectively eliminating the need for cosmic censorship. Example: the concept of a quantum bounce in loop quantum cosmology replaces the Big Bang singularity with a transition from a prior contracting universe to the expanding universe we observe. Analogy: quantum effects near singularities are like microscopic details on a photograph that become visible only when magnified, altering the apparent continuity of the image. Mathematical studies of the Einstein field equations continue to test the validity of the cosmic censorship hypothesis. Numerical simulations of collapsing matter under extreme conditions provide insights into whether event horizons always form to shield singularities. In some cases, deviations from idealized conditions suggest the possibility of naked singularities, but such scenarios often rely on highly specific or unphysical assumptions. Additionally, Penrose's hypothesis has inspired mathematical formulations of spacetime structures, including Penrose diagrams and causal sets, which visualize the interactions of singularities, event horizons, and external spacetime. Example: numerical simulations of collapsing dust clouds have demonstrated that event horizons form under most realistic conditions, shielding singularities from view. Analogy: mathematically exploring singularities is like running computer simulations of a dam break. Understanding how water behaves helps predict whether it will flood or remain contained. The cosmic censorship hypothesis has deep philosophical implications for our understanding of the universe. If singularities are always hidden, it suggests that nature enforces a cosmic veil to preserve the predictability and coherence of physical laws. If exceptions exist, they may point to new physics beyond general relativity. Cosmologically, singularities raise questions about the ultimate nature of spacetime and the universe's beginning and end. Whether the Big Bang singularity was hidden or replaced by a quantum phenomenon remains an open question, as does the fate of the universe in potential future singularities. Example: debates around the multiverse hypothesis and black hole information paradox often hinge on the nature and accessibility of singularities. Analogy: cosmic censorship is like a storyteller ensuring that the most perplexing parts of a narrative remain unseen, leaving the audience to ponder the mystery without disrupting the coherence of the tale.